Okay, John, would you feel comfortable having a little chat about your background in CCS while we wait for people to join? Yeah. So if I actually introduce you as our Director of UKCCSRC and Professor of CCS at University of Sheffield. So
thanks. Yeah.
About your background.
Well, so I'm a mechanical engineer with a background in power plants. I started working on CCS about nearly 20 years ago now. And I seem to have been doing actually very similar things all the time because CCS has had a number of starts and a number of stops. Hopefully this is the last one. But we have actually made quite a lot of progress in a number of areas. We've got a pretty good basis globally now of experience, and I'm looking forward to the UK actually getting some steel in the ground and really changing the whole pace of carbon capture and storage as we do that, which will make a big contribution globally. So I think I'll start showing my screen now, if you can stop sharing there. Okay, so this is the third seminar in the series, looking now at some technical aspects of carbon capture. In this case, carbon capture with post-combustion using amines, which is the technology that will get used in particular in the UK. So I'm going to give a lecture covering quite a lot of ground. The slides will be available on the website afterwards. And the slides, because of that, the slides are fairly complicated. I wanted them to be able to stand on their own, so they've got a lot of information on them. When we're going through the different topics, I'll point out what I want to talk about, but I won't necessarily talk about everything on the slide. So we're going to look at the basic principles of amine post-combustion capture, go through some experience to date on two projects, Boundary Dam in Canada and Pedro Nova in the US. We'll look at some of the problems and key priorities based on the experience of those projects. We'll look at a number of examples of proposed new amine post-combustion capture applications in the UK and elsewhere, and then a little bit about how future UK power plants might operate under the dispatchable power agreement. A lot of this material, in fact, more detail than we've got here, is going to come from the BAT review for new build and retrofit post-combustion capture for power and CHP plants on gas and biomass, which the UKCCSRC has been preparing for the Environment Agency and the other regulators in the UK as part of the permitting process for new plants. And that, I think, will be released later this week on this location. And the guidance document will be released as well at the same time. So Hannah Chalmers showed this, this slide in the kickoff seminar, looking at different ways of capturing carbon dioxide. And in this talk, we're going to be looking at post-combustion capture, which basically operates at this point. You take a standard flue gas, essentially business as usual flue gas, and you capture the CO2 from it. This can also give you effectively carbon dioxide removal from the air if you're using biomass. And this is a power application shown here, the way it's laid out. You can also use post-combustion capture on a lot of industrial processes, and we'll talk about those. So it's a pretty useful technology. It's fairly mature. It looks like it will be deployed in fairly large amounts in the initial rollout. And as we can see, as I'll show you later, it's likely to keep on going. It's a fairly competitive technology as far as we can see. So how does it work? Well, there's really only one thing you need to remember about amine post-combustion capture, which is that amines bond to carbon dioxide when it's cold, and they release it when it's warm. And that's essentially how everything works. there is a little bit of finer detail, some chemistry here I'm not going to go into, you can look at afterwards, but one thing you need to remember is for some amines, one molecule of CO2 reacts with two amine molecules. And for other amines, one molecule of CO2 reacts with one amine molecule down to the chemistry of the amines. And that means that amines behave in different ways. A basic amine, this is monoethanolamine, MEA, universally known as. These are two carbons. This is an OH group. If it didn't have this NH2, which is basically ammonia, on it, it would be ethanol. It would be drinkable. So the simplest amine is just ammoniated alcohol, a relatively common substance in nature as well. You can get more complex amines, and they will hold more CO2. Some of them will react faster, but they all come with different characteristics, and you have to take them in the round. So the way you use this characteristic of it grabbing CO2 when it's cold and releasing it when it's hot is you have this this circulation diagram, a figure of 8. So we circulate amine in this figure of 8 pattern, and the flue gases go through an absorber, which is a large tower, can be as high as nearly 50 meters, filled with corrugated packing, stainless steel, but it looks a bit like corrugated. There's a corrugated cardboard, which gives a good gas liquid contact area. The whole thing's run at atmospheric pressure. And flue gases containing fossil CO2 or CO2 we want to capture come in at the bottom. And what we call lean solvent, lean amine, which is maybe got about 0.2 molecules of CO2 per molecule of amine, so it's not saturated, comes in at the top at a relatively low temperature, maybe 40 degrees centigrade. And that trickles down over the packing, the flue gas flows upwards, and as a result, you take out all or most of the fossil CO2, and that flue gas is then vented to the atmosphere. And then the amine, having picked up the CO2, becomes what's called rich. Depending on the type of amine, it'll have between 0.4 and 0.8 molecules of CO2 per molecule of amine, and it leaves at a slightly higher temperature. Then to regenerate it, we have what's called a stripper, which is another large tower, probably not quite as big, well, won't be quite as big as the absorber because it's operating at pressure, which reduces the volume, typically somewhere between 2 and 5 atmospheres, depending on the amine. Before we put the rich amine in at the top of the tower, it's heated up in something called the cross-flow heat exchanger. And so that heats it up to about 140 degrees centigrade. It goes in the top, it trickles down over packing, and steam comes up from the bottom of the stripper, produced by boiling off water vapor, by condensing steam, saturated steam in heating tubes. And that splits the amine CO2 bonds by raising the temperature, and it also provides steam to help carry the CO2 away. And so after that, the lean amine leaves at the temperature at the bottom of the stripper, somewhere between 120 and 150 degrees C, and high purity CO2 is released, better than 99% purity CO2, mixed in with water vapor, and the water vapor is condensed, and the CO2 goes on to be compressed, transport and storage. So that's the whole process. The equipment's a bit more complicated than that, but the basic concept is very, very simple, and it's been in use for nearly 100 years. I said post-combustion capture was fairly competitive. This was an assessment done for bays by Wood, looking at different types of power plants with CO2 capture. So this is a gas turbine combined cycle plant without capture and paying quite a lot of money for CO2 emissions. This is similar gas power plant, but with post-combustion capture. And at the carbon price that was assumed, it's more economic to capture the CO2. Now, compared with other options, producing and burning hydrogen is less efficient and higher capital costs, so that's significantly more expensive. There are applications for that. We'll talk about it a bit more in the next seminar. If you can store the hydrogen and produce it in a relatively small plant which runs all the time and feeds the storage, and then you draw off the storage infrequently to meet a peaking load, it can be competitive. But for any reasonable load, certainly above about 50% load factor, post-combustion capture will be cheaper. Also, compared to supercritical CO2 cycle, Allen cycle, we estimated that it would be competitive, and also compared to using molten carbonate fuel cells. Obviously, these technologies are nowhere near as developed as these two, so it's not entirely clear what the actual cost and performance will be. But nonetheless, post-combustion capture looks to be a pretty reasonable option, even though it has, as I say, been around in some form for quite a long time. Also true for coal power plants, post-combustion capture beats oxy-fuel and integrated gasifier combined cycle with CCS, and also for biomass. Just be aware, these costs don't include any credit for the negative emissions you get from BECCS, so they look high numbers. But anyway, post-combustion, biomass plus post-combustion, is competitive on cost between a sort of theoretical biomass plus oxy-fuel. This plant hasn't really been developed yet, and very competitive compared to biomass gasification to hydrogen to generate power. Even though the efficiency is higher, the capital cost is just expected to be significant, and there may be some technical issues as well. So bottom line from that is post-combustion capture looks like it's going to be around for a while, particularly as it gets developed, and costs will inevitably come down a bit. One of the reasons that post-combustion capture works so well is that you can supply heat to regenerate the solvent very effectively. You need quite a lot of heat, but it's at low temperatures, so it's very little value for generating electricity. And as I said, you're condensing steam from the power plant in heating tubes, and that steam was going to be condensed anyway in the power plant steam condenser. So you typically get 4 or more units of heat for every unit of reduction in electricity output. It also means to get that ratio, you need to run a CHP plant if you've got a non-power application in industry to get the same benefit. And you will also, as well as that heat, need some electricity to run the fans, and in particular the compressor for the CO2. Just to illustrate that, this is the energy, 100 units of energy going into a gas turbine on a gas turbine combined cycle. It's a slightly older unit, produces 37 units of electrical output. The rest of it, the energy, is heat in the exhaust gases, which go to the heat recovery steam generator, waste heat boiler. Most of that ends up as energy in steam, but the steam turbine can only extract a bit less than half of that, about 40%, on a plant without capture. And the rest of the energy goes to this thick grey arrow to the condenser. When you take out some steam for a post-combustion capture unit, now this red arrow, you take out about half the steam near the back end of the steam turbine. The electricity output goes down a bit, about a quarter of the energy going to the steam, and a lot less steam goes to the condenser. So this actually makes it a very efficient plant. This steam turbine process and the condensation, as you can see, in some ways is not very efficient. It's as efficient as it can be thermodynamically, but it was going to throw away a lot of heat anyway. You might as well throw it into the post-combustion capture plant. And it's quite hard for people to get this because they don't often look at linking heat supply with efficient processing of fuel energy. But once you do link that, and this is what I was basically working on 20 years ago, once you do link that, post-combustion capture looks very, very good. Some examples. This was the first post-combustion capture plant in the world at the Boundary Dam Power Plant in Saskatchewan in Canada. It's called Boundary Dam because it's very close to the border with the US. It's a fully integrated system, so it takes advantage of the efficient steam supply. The unit 3 was upgraded. It's an old unit, but it was pretty much turned into a new condition. And a big duct was added coming around from this stack at the back. Duct you could drive a bus through. You can see cars here to get an idea of the scale. To take the CO2, first of all, to a flue gas desulfurization unit, which is just out of sight here, then into this big absorber here, and the flue gases come out this stack at the top. The CO2 in the solvent is released in this stripper vessel here. Everything's hidden in a box. It gets very, very cold in Saskatchewan in the winter, so you're not able to put plant outside. This unit captures about 90% of the CO2, and it's about 1 million tons of CO2 per year. I'd say that was the first one. Second large unit on flue gas was at Pedro Nova power plant in Texas, much warmer. You can see everything's outside here, they don't worry. This a bit bigger, captured about 1.6 million tons of CO2 per year. Here's the absorber again, and the stripper. Here's the flue gas duct, in this case a round one, taking the flue gas to the flue gas desulfurization unit, which is required because this is a coal plant. And they didn't take steam from the power plant itself. They had a combined heat and power unit powered by natural gas over here, natural gas relatively cheap in the US. So this unit became operational in January 2017, and it shut down in mid-2020. I'll discuss that a little bit in a moment. So experience from these two units is that the operating costs, and this is effectively the levelized cost of capture here, the total estimated cost for capturing CO2 can be quite high. So you have a capital cost element, which is the light blue, quite high for Boundary Dam. It's an expensive place to build things, Saskatchewan. And it was a small plant. Much lower for Pedro Nova. You get good productivity in Texas from labor. But as well as the capital, you've got running costs. So you've got a fuel cost, the extra fuel that's burnt, relatively small contribution. You've got some fixed operation and maintenance. And then, fairly surprisingly, there was a very, very large element for variable operation and maintenance reported for Boundary Dam by the Global CCS Institute. And this is basically for replacing losses in the solvent and managing ways to keep it pure enough to operate. And as you can see from the text below, this would be expected to be of the order of $5 per ton, and it's well over 20. It's also relatively high for the Pedro Nova plant. Now, Boundary Dam is still running. I suspect they've got this cost down a bit, although it's probably still high. Pedro Nova isn't running, and I think the reason for that could be that if you have a look at the total variable costs, it's over $20 a ton of CO2, and this unit was sending its CO2 for enhanced oil recovery, and a ballpark figure for the value of CO2 for enhanced oil recovery is about $20 per ton. So even at reasonable oil prices, they were low for a period in 2020, but they're back up again now. Even at reasonable oil prices, this plant doesn't seem able to recover its operating costs under the present sort of subsidy regime, which could explain why it's not operating. So some key priorities in the light of, I guess, what you have to see as problems. Obviously, they're successful in that they ran, but they're not as successful as we would have liked them to be. The first point is, I think, when I'm saying it's not clear what's happened. There have been reports, obviously, on these plants, but many of the key details are omitted on the grounds of the solvent being commercial and requiring confidentiality. So we just don't know what's happened. You're looking for the details in obscure places and certainly not getting the full picture. However, it is pretty clear from evidence given to Saskatchewan Government Committee that higher than expected solvent management costs were incurred. And as I say, we do know that Pedro Nova isn't working. So they must have higher running costs than the revenues. So obvious response for the first problem is, if you've got a project that's only possible because of government support, require full disclosure of key features and the results, especially the problems, to allow industry learning by doing. It isn't necessarily giving away all the secrets, it's just saying, did it work? How did it work? What were the numbers? I think quite often these are kept secret because, particularly when you get a problem, people are embarrassed, not unnaturally. But if we don't learn from the problems, they'll keep on being repeated. And then, particularly on this solvent management issue, it's important to test properly to avoid what I call solvent-related surprises, and also to have some backup options in case they still happen. And what you see is that when you get a guarantee for solvent performance, it's of the same order of the license fees. It's probably less than 10% of the total project value, and it really doesn't compensate for the potential problems. So the only assurance that things will actually work is to do extended testing on a realistic pilot plant, ideally using the actual flue gas from the plant that you're going to retrofit. If it's a retrofit or a very similar plant. And you need to test for about a year, because it can take quite a long time for these degradation reactions in the solvent to happen. It's important that you demonstrate, excuse me, that you can what's called reclaim the solvent, which is separate the good solvent from the impurities. That's a very important part. It's often omitted actually from sort of research type pilot tests. And also, it's very important you can change to an alternative solvent if you're having problems. You'd want to do this anyway because solvents are going to be improved, but you might need to do it in a hurry if your costs are too high. And this is apparently more of a commercial issue rather than a technical issue. So boundary dam, in fact, I believe was designed for alternative solvents, but they found they were tied up by contractual arrangements and couldn't change. So solvent selection criteria, it is a fairly important part of the overall process to get a successful project. Health and safety is your first consideration, and absolute standards have to be met. And what appears to be one of the more interesting areas is conversion of trace emissions of amines, parts per million coming over in the flue gas, but obviously relatively noticeable amounts when you've got very large plants, and particularly when you've got multiple very large plants, as the UK is expecting to have. And these traces of amines can be converted to nitrosamines in the atmosphere, and those are highly carcinogenic, and we've got very low environmental loads for those. And that at the moment has to be assessed by modelling. The techniques for modelling are still being developed, and when we get larger plants, we'll be able to do more measurements as well. So this is an area of interest, and John Henderson from the Environment Agency will be talking about environmental aspects of CCS later in the series. You also want to be able to capture a lot of the CO2 that's coming out, and we're looking at now going above 90% capture. Overall costs are obviously important. We want to get the costs as low as possible. There's a lot of different elements for those, which I'm not going to go through, but it's a package. And then, as I say, there's opportunity costs. You want to be able to modify and upgrade the plant in service to correct faults. That's an important thing to be able to do. And you want to be able to take advantage of learning. And these plants will be around maybe for 20, 25 years or longer. They will be upgraded in service, and you want to be able to do that. Some trade-offs. I mentioned that you get different properties. So typically, primary and secondary amines, types of amines, have higher rates of reaction. Monoethanolamine, MEA, is one of the oldest in use, and it's got a high reaction rate. But it can only get this one 1 to 2 stoichiometry with CO2, so it can't latch onto as much CO2 as some of the other amines, which bind 1 to 1. Another type of amine, tertiary amines, have high capacities, but the kinetics are lower, so you try and use them in blends. So you've got a lot of permutations, a lot of trade-offs. But then from a health and environmental safety perspective, MEA is biodegradable, so it's often found in nature. Some other amines are more toxic and not so easily biodegraded. The not primary amines, but secondary amines can react with NOx in the flue gas to form nitrosamines, and the reactivity varies with the amine structure. So you have a fairly complex balance of factors to take into account when you're selecting which amine to use. So this I think, conversion in the atmosphere is the main consideration in getting satisfactory environmental performance. As I say, it's too low to measure easily. It has to be estimated through modeling. You need to look at the amount and type of amines coming out in the vented flue gas, and you've got to look at the amines from other plants in the same area. You've got to look at what's in the atmosphere in terms of NOx, and you've got to look at atmospheric conditions. So people will be doing site-specific modeling to work out how much is safe to emit from a plant. And then you can do a lot on the plant itself to control what comes out. So I've put this in the PC emissions control triangle. So first of all, select the amine, which will give you a mix of properties, reduce degradation and impurity addition rates, and accelerate removals. So you keep your amine nice and clean. That helps a lot. You then trap potential emissions at the absorber exit. You can do an awful lot there with washing it with an acid solution. And then finally, you dilute and disperse the emissions by making sure that you emit them high enough and with a flue gas stream that's warm enough to rise and mix. And then there's a lot of detail in there which I'm not going to discuss, but it's there to look at afterwards. One of the areas that's received a lot of attention is the energy that different solvents require and the effect this has on the overall cost. But as I say, it's a complete package. And when you look at the estimated costs, this is from a study done for the World Bank, a retrofit to a gas turbine combined cycle plant in Mexico. If you take a range of commercial solvents, these are the ones that could be in use now. Basically, there's no difference between the numbers, and indeed, they're not much cheaper than monoethanolamine at 30%. We'd be looking at using 35% by weight now, which would make it a bit better. So it does seem that, at least superficially, there isn't a lot of difference between solvents. The differences will come in the fine detail, and I think particularly in terms of the environmental performance. Okay, some examples. We might see in the UK, this is one that's actually happening. Post-combustion capture plant at Tata Chemicals, Northwich in Cheshire. Bayes kindly gave 4.2 million towards it. It'll capture 40,000 tons of CO2 per year, so it's quite small, a 25th of the million ton a year size, but nonetheless, it looks pretty big. It's probably about as high as a real absorber would be, about 50 meters. This was supplied by Pentair Union. It uses 35% by weight MEA, and this is continuously cleaned, continuously reclaimed. Pentair Union have built over 20 plants around this size, mostly using natural gas sources. So this will be running soon. Really looking forward to seeing that. However, the big plants in the UK being planned, places like Teesside, Humberside, post-combustion on large gas turbines, they sort of follow on from a study that was done by the Energy Technology Institute a few years ago, looking at bringing the cost of gas power with carbon capture and storage down by building large units with multiple turbines, in this case 5. I think probably more realistic to find 2 at the moment. So we've got a gas turbine here. This is open up. This is the actual turbine, the gas turbine. This is the heat recovery steam generator. This is a stacked event when you're not capturing. and then this is going through to the capture unit and the stripper all combined here. And this is the cooling. And as I say, there's 5 units shown here to get economy of scale. You can look at the report for this. It's available now. It's quite a lot of documents, and also an even more detailed feed study, front-end engineering design study with about 200 documents for a 1 million tonne a year retrofit that was in fact never built in Norway, is available on our website. So you can get quite a lot of detail if you want to go into that. Another application is a new build or retrofit on biomass. This is a post-combustion plant that was looked at in a feasibility study, not for a biomass plant, but for a brown coal plant, similar properties in Australia. One of the things is it doesn't have a flue gas desulfurization plant. This brown coal had very little sulfur in it, same as biomass. So you're taking out sulfur, which would react with the amine in a direct contact cooler. You're getting plume buoyancy by heating the flue gas at the top. And because it's a dirty flue gas, you want to keep your solvent clean. So you're running continuous reclaiming. This requires heat, but you recover the heat by putting the reclaimed solvent vapor and steam directly into the stripper where you need the heat anyway. Again, this is available. It's an open access study because it uses MEA, and you can download it from the reference given if you want to have a look in more detail. Another application I think we're quite likely to see a number of is CO2 capture from incinerators. This is one that's been built at Dweven on an AVR plant in the Netherlands. This is the absorber, the stripper, and then you've got the direct contact cooler and a wash column put together here. This is 100,000 tonnes per year. It's sold to the greenhouse industry. And the estimate is that in Netherlands, they were able to capture about 2 million tonnes a year of CO2 from the incinerator sector, which is quite a significant part of their overall strategy. And there's a number of other plants being built, some with proprietary amines, some with MEA. And you'll be getting an overview of the Netherlands CCS plans on the 29th of July. But as I say, hopefully we'll be seeing some plants like this on incinerators in the UK. Another possible application is post-combustion capture on a steam methane reformer. This is a study, same study actually as I showed earlier, that Wood did for Bays. A steam methane reformer uses burners venting to atmosphere. It's shown here on the steam methane reformer. And so you put post-combustion capture on those, on that flue gas to capture the CO2. We'll talk about this more in the next lecture, but the syngases containing hydrogen come out, you refine them to get as much hydrogen as possible, take out the stuff you don't want, put it back in the burner. So all of the carbon basically ends up in the flue gas and you capture it. If you just capture carbon from the process and not from the flue gas, you can get maybe between 55 and 70% of the CO2 captured. There's a reference for that. But if you capture from the flue gas, you're not limited by that to that number. You can get up into the high 90s. Just a bit of a plug for the UKCCSRC. As part of our core research program, we've actually looked at improving on this by using a gas turbine to provide flue gas to these burners in the steam methane reformer to substitute for the air. And this allows you to recover some of the heat, and also it allows you to capture the CO2 from both the steam methane reformer and the gas turbine together, which is expected to reduce overall energy consumption and cost compared to building separate units. So this is something that industry has looked at. Whether it'll actually happen, I don't know, but it's a fairly sound basis for achieving some cost reduction if you want to produce power and hydrogen at the same time. Obviously, another application, big application, is industry. As I said, post-combustion capture can be applied to any flue gas. So you've got lots of different sources, refineries, certainly being looked at, glass furnaces, cement kiln, limestone kilns, as I say, any flue gas source. If you're retrofitting though, there's space issues. You do have to worry about the flue gases being hotter than the amine plant can take. They need to be at about 50 centigrade. There may be SOx and NOx. As I say, you've got to be able to supply heat effectively. Waste heat is best, but use a CHP if you can't do that. One thing you might do is separate the absorber and the stripper, so you have multiple absorbers on different stacks on a site and then share a common large stripper. You can also, people will substitute hydrogen for fossil fuels to avoid post-combustion capture, but this won't work with processes that produce CO2 as part of the manufacturing, which is cement and lime. And also if you're in a refinery or steelworks, these burn waste fuels from the process. And if you use hydrogen instead, the waste fuels are still going to be burnt somewhere with CO2 capture. So this is an example of a plant. This is now in Norway on the Breivik cement plant. The coloured bits are what they're adding. This is the absorber. This is the stack on the absorber. Great big stack to get good dispersion. This is a relatively small unit again, 400,000 tonnes a year. It only captures 50% of the cement plant's emissions. I don't know how long they'll be able to carry on doing that because they're only using waste heat from the plant. They would need a CHP unit as well to be able to capture all of the CO2. Special feature over here is the loading dock to load up the ships, to take the CO2 several hundred kilometres around the Norwegian coast to their storage site. You often hear people in the UK saying, oh, well, you know, we've got a cement plant. It's remote from storage. Well, very few are as remote as this site in Norway. However, it is quite useful being able to get big vessels in to take the CO2 away. That's very helpful. So this is the core of Norway's Longship CCS program, and we will be hearing about the Norwegian CCS program later too. For power plants operating under the dispatchable power agreement, it's a good idea to operate at as high a capture level as possible. And again, a bit of a plug for research that we've been doing. It looks as if you can get up to even 99% capture, in this case with MEA, but I think with other amines as well, some of them anyway. And 99% capture on a gas turbine flue gas is actually all of the fossil CO2. The 1% is what came in, last 1% is what came in with the air. People have shown very high capture levels at a test centre in Norway, test centre Mongstad, so it does look like it's feasible. And in discussions with industry for the BAT process, it looks like 95% will become design level. So the plant will be designed for 95%, and then, as I say, under the dispatchable power agreement, it'll probably operate as high, the highest capture level as it reasonably can, because it'll make a little bit more money that way, as indeed it should do. The other thing is that you need to be able to capture CO2 at a high level while the plant's starting and stopping, because the dispatchable power agreement will penalise plants if they emit CO2 at any time during their operation, perfectly reasonably. And the issue there is that the gas turbine can start up very quickly, but it takes some time to generate steam in the heat recovery steam generator. So you've got CO2 coming out of the gas turbine, going through the absorber here, but you won't be generating fresh solvent in the stripper. So the solution here, which has been proposed in a report for BEIS, BEIS commissioned on startup and shutdown times of power CCUS facilities, it's relatively simple. It's to provide some storage of lean amine and some storage of rich amine. And until you can regenerate your solvent, you just run amine from one tank to the other through the absorber column. It picks up CO2. And then when the plant's up and running, over a period of time, you regenerate this captured solvent in parallel with your normal operation. So that's, again, I think we can achieve very high capture levels. It will pay for the plants to do that. So quick conclusions. Post-combustion capture plant performance and cost is expected to be competitive to other options. There's some lessons to be learned from the previous two large projects. if you get government support, full disclosure is a good idea to allow industry-wide learning by doing and test properly and have some backup options in terms of being able to change solvent if you still get solvent problems. There's a trade-off in solvent selection. There's no ideal combination of amine properties, but health and safety have to take priority. There's limited public domain information on proprietary solvents, but some evidence that actually, at least on simple comparisons of energy, capital cost, whatever, they get similar numbers. Although, as I said, we do have evidence that at least one project showed that you get surprises on details like operating costs, which are expected to be low, but can turn out a lot higher than you expect. Post-combustion capture, though, it's got very many potential applications in the UK and globally, and I suspect China, well, sure, China will have vastly greater amounts of post-combustion capture on its coal plants than any the rest of the world put together. And high levels of capture, 95% and above, are becoming the norm to meet net zero requirements. And that's something that's changed relatively recently, but it shows that the technology can be improved to meet new demands. So that's it. Thank you. Any questions?